everybody, welcome back to the lab. We've been spending a lot of time in DL talking about electric circuits, and we've seen some examples of circuits with single batteries and single circuit elements. But of course, most real-life circuits are much more complicated than this, involving perhaps multiple sources of power and multiple elements such as resistors or light bulbs. Because of this, there's a few rules we need to learn about in order to analyze these more complex circuits. We'll start with some definitions, particularly the difference between series and parallel components. Series and parallel are the two main ways that components can be aligned in a circuit. Series looks like this. There's a single path for the electricity to take from the left to the right. It must pass both through this resistor and this resistor. It doesn't get a choice. This is an example of two resistors in parallel. The current flowing in from the left has to make a choice when it gets here whether to go up through this resistor or down through this resistor. It cannot go through both, unlike in the series case where it has to go through both. In practice, this means that the current is going to split between the top half and the bottom half. This split may or may not be even, and we'll see how we analyze this in a few minutes. When analyzing these types of circuits, there are two rules we should keep in mind. The first is known as the loop rule. We've actually already seen this rule in practice in a previous example, though we perhaps have not called it that. The loop rule just says that if you start at a point in a circuit and go around a closed loop and return to that same point in the circuit, your total change in voltage must always be zero. We saw this for the full circuit case with a single light bulb and a single battery, but it works equally as well for any loop, regardless of the elements in that loop. In practice, this block of resistors is connected to a much larger circuit, but we can still apply the loop rule just around this loop. It works just fine. We can, of course, apply the loop rule around any loop we find in the circuit, no matter how complex the circuit is or how many loops exist. The second rule is called the junction rule. The junction rule just says that the current going into a junction has to equal the current coming out of a junction. A junction is just a location in the circuit where the path splits, such as here. There are two routes for the current to take. The junction rule just says that if we calculated the current coming in through this wire, it would be equal to the amount of current flowing through this wire plus the amount of current flowing through this wire. It also says that if we were able to calculate the amount of current flowing through this wire and the amount of current flowing through this wire, and then added them up, that number would be equal to the amount of current flowing through this wire. Next, we need to know how resistors interact in a circuit. It's actually possible to use the loop rule and the junction rule to determine the equivalent resistance of resistors in series or in parallel. Take this case as an example. We have two resistors in series. If we calculated what the total resistance of the two together were, we could imagine that these two resistors were just a single resistor with the equivalent resistance. Well, what is that equivalent resistance? If we want to know the equivalent resistance of two resistors in series, we just add them up. It's that simple. If both of these resistors have resistance R, then the equivalent resistance of the two resistors together is just 2R. This works for any number of resistors in series. If we had a third resistor here, we just add that resistance on to find the equivalent resistance. Equivalent resistance in the parallel case is a little bit more tricky. It turns out that it's not the resistances that add in the parallel case, it's the inverse of the resistances. If both of these resistors had resistance R, we would find the equivalent resistance like this. Instead of adding the resistances, as in the series case, we're adding the inverse of the resistances. Let's solve this equation for Req and see what it tells us about the equivalent resistance of this block of resistors. At this moment, you're probably scratching your head. You're saying we took two resistors, added them together, and got a resistor that had less resistance than either of the resistors did on their own? It turns out the answer is yes. This is exactly what happened. When you place two resistors in parallel, you end up with an equivalent resistance that is less than either of the two resistors would be on their own. This is just a fact about the way that parallel resistors work together. If we had a third resistor in parallel, say like this, we would modify this equation by just adding the inverse of the resistance here. Let's use this information to solve two problems from your FNTs. In this circuit, we have two batteries and three light bulbs. Both batteries have the same voltage, which we'll call epsilon, and all the light bulbs have the same resistance, which we'll call R. We're interested in a few things. We want to know the change in voltage across each of the light bulbs, as well as the current through each of the light bulbs, and the total current flowing through the circuit. To do this, we're going to use the loop rule. There are two closed loops that are going to be useful to look at in this problem. The first one is this loop, and the other one is this loop. Let's start with the larger loop. We'll take our beginning and end point to be this corner, and we'll trace the circuit around like this. The loop rule says that a change in voltage around a closed loop is 0. We're also going to need Ohm's law, which looks like this. Notice in this case, this epsilon and this epsilon are not the same epsilon. This epsilon refers to the total increase in voltage from batteries. The loop rule tells us that around a closed loop, this number is 0. Let's go around this loop and see what terms appear. We have two batteries, so immediately we know that as we pass from here to here, we have an increase in voltage of 2 epsilon. Remember again, this epsilon and this epsilon are not the same. Next, we pass through this light bulb. The resistance of the light bulb is just R, and the current is what we're interested in. So let's plug that term in. Solving for I, we get the following. So the current passing through this light bulb is 2 epsilon over R. Now let's do the same thing, but for the smaller case. We want to know the current passing through these two light bulbs. We'll apply the loop rule again, but instead of going around the large loop, we'll go around the small loop. First thing we need to ask ourselves is what is the equivalent resistance of these two resistors? If you said 2R, you're right. These two light bulbs are in series, so their resistances just add. Writing this equation out for the small loop gives us the following. So the current flowing through these two resistors is just epsilon over R. Now we also might want to know what the total current flowing through the system is. It turns out this is extremely straightforward. We've actually already found this. Remember the junction rule. If we apply the junction rule to this point, it tells us that the current flowing down into this junction has to be equal to the current flowing through this path plus the current flowing through that path. But we've already found those currents. They are 2 epsilon over R for the lower path and epsilon over R for the higher path. So the total current that's flowing around this circuit is just this current plus this current, 3 epsilon over R. Another thing we might like to ask is what the voltage difference is across these individual pieces. It turns out this is also straightforward if we just use the loop rule. Going back to the larger loop, we know that the batteries increase the voltage by a total of 2 epsilon. The loop rule tells us that if we get back to the same point we started, we should have a total change in voltage of 0. So if the change in voltage across the batteries is 2 epsilon, then the change in voltage across this resistor must be negative 2 epsilon, such that when we get back to here, we get 0. The same is true for the smaller loop, but there's one key difference. Instead of having just one element, we have 2. So what is the change in voltage across the individual light bulbs in this smaller loop? Your intuition probably tells you that since these light bulbs are exactly identical, half of the voltage change happens across this light bulb, and the other half of the voltage change happens across that light bulb. And you would be right. We know that the total change in voltage across both of these light bulbs has to be negative 2 epsilon. Remember, we get 2 epsilon from the battery, so in order to get to 0, when we get back to our original starting point, we need a change of negative 2 epsilon across these 2 resistors. Since the resistors are identical, it is correct to say that each of the resistors have a change in voltage of negative epsilon. Next, let's look at another case that is a little bit more complicated for a few reasons. In this example, the batteries again both have the same voltage and the light bulbs all have the same resistance. However, in this case, we have a single light bulb in series with 2 light bulbs that are in parallel. We want to ask ourselves the same questions, namely, what is the total current flowing through the circuit, the current flowing through the individual pieces of the circuit, and the change in voltage across the individual pieces. Let's start with total current. To do this, we need to know the equivalent resistance of all of these resistors. We'll start by finding the equivalent resistance of this block of 2 resistors in parallel. As we've discussed, when 2 resistors are in parallel, it's the inverse of their resistances that add. So finding the equivalent resistance looks like this. We can now imagine replacing these 2 light bulbs with a single light bulb with resistance R over 2. Now we have to ask ourselves, what is the equivalent resistance of these 2 light bulbs? We know that for resistors in series, the equivalent resistance is just the resistances added up. So this has a resistance of R, and this is a resistance of R over 2. So we can replace those 2 resistors with a single resistor with resistance 3R over 2. We now have enough information to find the total current in this circuit just by applying the loop rule. We only have a single loop, so there's no ambiguity about what we're doing here. Remember, the loop rule just says that if we go all the way around the loop once, our total change in voltage will be 0. We'll combine it with Ohm's law just like we did in the previous example. And there we go. We found the total current flowing through this circuit. It is 4 epsilon divided by 3R. Again, we just use the same rules that we've been seeing this whole time. By setting up the circuit like this, it makes it very, very easy to describe it using the loop rule. However, we also want to know the resistances and changes in voltage across the individual circuit elements. To figure that out, we need to go back to looking at the complete circuit with all its components. Next, we want to know the current through these individual resistors. This is the total current in the circuit. We know that all of that current must be passing through this bulb. However, once the current gets to here, it splits into 2 paths, and so we want to know how much of the current takes each path. Because these 2 resistances are the same, this problem is actually straightforward. Your intuition may say that if the resistances of these two light bulbs are the same, then the current will split equally between them. That intuition is correct. The fact that these two light bulbs have the same resistance means the circuit should not be able to tell which direction is which. The only way for this to be true is if the current splits evenly. So we know that the current through this light bulb is 4 epsilon over 3R, and the current through each of these light bulbs will be exactly half of that. The last thing we want to know is the change in voltage across these individual circuit elements. Let's start with this one. We've been using Ohm's law and the loop rule together in a lot of cases thus far, but there's no reason that we have to do that. We can always apply Ohm's law between any 2 points in a circuit, not just around a loop. So let's apply Ohm's law across this light bulb. Ohm's law just says this. Epsilon just represents the change in voltage due to any battery between our 2 points, and IR is just the change in voltage across any 2 resistors. If we apply Ohm's law between this side of the light bulb and this side of the light bulb, this first term goes away because there are no batteries between those 2 points. And there we have it. The total change in voltage across this light bulb is negative 4 epsilon over 3. Next, we want to know the change in voltage across these resistors here. There's a rule that we can actually use to simplify this part of the problem. It turns out that if 2 elements are in parallel, then the change in voltage across them must be the same. So if we can calculate the change in voltage across one of these resistors, we found the change in voltage across both of them. So to find the change in voltage across these individual light bulbs, we just do Ohm's law a second time, except instead of using the entire current, we only use the amount of current that's flowing through each of these light bulbs. So our change in voltage across this light bulb and across this light bulb is just negative 2 epsilon over 3. To check our math, let's just make sure that the loop rule gives us the correct answer. If we start here and go all the way around, we expect the change in voltage to be 0. We've now found the change in voltage for all the individual circuit pieces, so if we add them up, they should get 0. Going from here to here, we get an increase of 2 epsilon. We continue around the circuit until we get to this light bulb. When we cross this light bulb, we get a change of negative 4 epsilon over 3. 2 epsilon minus 4 epsilon over 3 is 2 epsilon over 3. Next, we either take this path or this path. No matter which path we take, we get a change in voltage across the light bulb of negative 2 epsilon over 3. So we have 2 epsilon minus 4 epsilon over 3 minus 2 epsilon over 3, which just equals 0. And so the loop rule shows us that our numbers work out. In most cases with circuits, there are multiple ways of analyzing the circuit to get the correct answer. You may find that the way that works best for you doesn't work best for your classmates. It just means you have different preferences about how to solve the problem. As long as you're getting the same answers, it doesn't matter. Any solution is equally valid.